Good call. I had not started recording, so thank you. I was about to do that, but I'll get it going now. But he's going to tell us a little about the work he does, and it's a good chance to see how this works in the real world, ask some questions, get some good answers, and just get a taste of all the things we've been talking about and how they work in the real world as we kind of get deeper and deeper into these development practices. I'm going to turn the floor over to him, but please let either of us know in the chat if you have any questions, and we'll address that when there's a good break. Anything else? Everyone good? Cool, then I will turn it over to Henrik now.
Thank you. Can you hear me?
Yes.
Yeah, so sound is working. I'll try to share my second screen. Sorry, I was in another meeting that ended 14 minutes past 1. So that's why I'm a bit unfocused here. Share screen. Can you see my second screen now?
We did, but then it stopped.
Yeah, it said it disconnected. Why was that? New attempt.
All right, I can see your screen again. And
that's better?
Perfect.
Okay, so thanks for the introduction, Greg, and also thank you for inviting me. Could you please be moderator? So if somebody puts a question that I don't notice, then you will interrupt me.
Yeah, absolutely, no problem.
Thank you. And to all of you, just interrupt if you have some questions or comments. Volvo is making various commercial products. As you hopefully know, we make Volvo trucks, but on the same, there we go, a platform, or as part of the same product line, we also make other kinds of trucks and other kinds of machines like buses and construction equipment. Especially the construction equipment has a very wide portfolio of products. There is Volvo Penta doing marine engines, but also gensets, meaning generators driven by a diesel engine for hospitals or remote areas and so on. Volvo Autonomous Solutions is the business area that puts together autonomous trucks or excavators or buses into a complete solution. So already on the first slide, you see this product line perspective that one have to take in a large organization in order to maximize the benefit of various components being developed. We are organized not only according to what we produce that you just saw, but we also have for the truck operations 3 divisions. One that do the technology, one called operations that do the manufacturing and putting together the trucks primarily, and purchasing is getting the components into the system, and much of what is in a vehicle is provided by suppliers, obviously. But I'm working here at Group Trucks Technology, and whoever of you that one day might join us would be working here, because This is typically where most of the in-vehicle software development takes place. And then whatever we do here is fed into the Renault branded trucks or the Mack branded trucks and so on. And to give you a flavor of different technologies, I should say also that we're a worldwide we have a worldwide footprint, with most of us in Europe and Gothenburg, some in France, and also in various other locations in Europe. Lyon in France and Gothenburg in Sweden are the two main engineering hubs. We have in North America and South America and Asia when it comes to product development. And then the other employees are partly for manufacturing and other things not related to product engineering. And looking at some technologies that you might see now or in the future is here. Maybe I'll come back to this slide later, so take a good look. These are different systems and components that are important for our customers. If we look at the more complete delivery, so to say, there's various conceptual tracks for autonomous use in mines or in refuse management. We have the driverless Vera truck and so on. So this is where the technologies that we develop end up eventually. But what you should take home, hopefully, or be strengthened in, is that your education and what you do now is really, really important for us. We need a good software architecture, and to do that we need software engineering competence. It's critical for us and for Swedish industry in general. And one topic that I will talk about today is modeling as an enabling technology, because of the complexity of the product and the needs we have on efficient development. So this is the bottom line. Why is this then so important? Well, we have a product. You saw the various autonomous solutions, connectivity, where we have more and more cloud and functionality that is outside the truck itself and that relies on functionality outside of the truck itself. We are going to a large fraction of our vehicles being electrified, both in hybrid setups and in full electrical setups. Every part of the Volvo range will have an electrical vehicle in the near future, which puts a big challenge on us. Not only on this high granular level are there changes, we're also changing inside the truck to have more capable control strategies. Instead of letting the driver push the pedal and the torque goes up, we want to have a layered architecture where the driver or the autonomous agent that moves around the vehicle says, I want a vector, I want the truck to go in this direction with that speed. And then that trickles down to decisions on the powertrain, on the chassis, and on the steering and brakes and so on. And with a layered architecture, we have a better opportunity to make energy optimal, safety optimal, performance optimal decisions for the behavior. And to support this, we need also to change the physical architecture to to have more computing power, more communication bandwidth between the different parts of the truck and outside the truck. We need to be scalable and composable so that one change in one end does not influence all the others, because then maintenance and correct development will be very difficult. So all of these product challenges are happening in parallel with various process challenges. So we want to be better at developing, for example, reducing the lead times, being able to deploy to the customers continuously, going from model years to a more iterative way of providing functionality. We want continuous integration so that during development, we can immediately make a small change and get the feedback on, was that okay, or did we break anything? Did we meet all our performance, quality, safety, and so on requirements? Quality must be maintained in spite of these changes. We want to reuse across our product line in the best possible way so that we don't miss the opportunity to use something in a Renault truck that was developed for a Volvo truck and vice versa. The different parts of a truck can be divided, for example, into domains. One is infotainment with short lead times and where a lot of things happen quickly in the market and in the vehicles, while brake systems or engines and gearboxes and so on, they are quite time-consuming to develop because of the safety and performance constraints. So these domains, they are different in many ways, but one is that these cycle times, they don't change as often, some of them. And there are different aspects that are important for a powertrain. Timing, control, stability, energy consumption, and so on is important, while in the infotainment or telematics domains, maybe ergonomics and look and feel and response time to the eye and so on is of more importance. So all of these different domains and different aspects that are interesting for them are managed by more than one team in more than one country. But in the end, it will only be one vehicle or a fleet or a family of vehicles, obviously, but it all must come together in a consistent way. So this is the background and gives you an indication of where does the complexity come from. So why do we want to use a model-based approach and a more and a better engineering approach? I think my title was Models for Automotive Embedded Systems Development. So what is the motivation for that? So traditionally, when doing product development, one have an early phase where one decide how to make a solution to meet a certain customer request. And then you can make very cheap or very expensive. Sometimes that correlates to being very basic and simple or being very capable and advanced, sometimes not. But regardless how, the cost flexibility goes down. As soon as you start to home in on a certain technical solution, you will end up with something that is, in this example, average cost. And the sooner you go to start of production, the less you can influence cost because of your choice of compiler or programming language if we talk software, or the kind of CPU or power supply or other things if we talk hardware. Design space is also something that is being smaller. In the beginning, you can do anything, but once you go towards start of production, you cannot change your solution that much, especially not for the red line here. As soon as you have chosen to have 4 wheels instead of having a bandwagon transmission, then you cannot do as much as in the early phase. But for software, it's rather big in the beginning, but flexibility stays rather big. Towards the end, when a certain memory size and processor family and all of that is selected, there is less room for making design changes. And finally, the amount of time traditionally that is spent. In the beginning, there is a small team doing design space exploration and thinking about the different opportunities. But towards the end, a lot of people are involved in doing the final implementation, doing testing and verification, preparing various test equipment and so on. This traditional approach has some drawbacks, obviously. We spend a lot of resources here, and only in the end we have a result. And this is the motivation for continuous deployment, to be able to have something that works, spend some time on improving it, and then we can, then we can deploy it to the customer, and then resources go down, we see how that went, and we can make a new iteration. But even when we do it in this way, iteratively and incrementally, we always need to keep track of the functional and non-functional properties and the cost and all of these desires that we have on the product. Only that instead of doing it in a slow and waterfall-like approach, like in the old days, we do it iteratively and incrementally with a much shorter delay until we start getting money out of the investment. So if we look at an example of how this comes together when it comes to testing, we have 2 options. One is to build a drivable truck and see how it behaves on the test track. Or we can make a virtual simulation-based approach. But in both cases, the purpose is to try to understand, is our design appropriate? But with the increased pressure here to have a short time between conception and delivery, we have to be ever better on our engineering activities. So for testing, that could mean that we do road and track testing, but only when we cannot simulate, and only when simulation is really impossible. And with difficult simulation, I mean, it's hard to simulate the fuel consumption or the stopping distance. It can be done, and we do it, but sometimes to get the real result, it's easier to just build a prototype and test. In other cases, simulation is even impossible. For example, if you want to run a clinic and ask people, what do you think about this new functionality? Then it's not good enough to give them a simulation tool. You need to put them in the driver's seat and ask, what do you think? What is the cab temperature, or what is the handling feeling when you go down the slope, and so on. So those are the first two reasons why road testing is used. But there is a third case, and that is there are vehicles out on the road anyway. Lots of customers drive their trucks. We have to move around our trucks to do maybe a endurance test. And while doing that, we could just as well do some software testing. And in that case, it's free. That driving time is being spent anyway. So, and the other alternative for testing would be to do it virtually. And there are many good reasons for that. For example, rare situations that seldom happen in real traffic is a lot easier to instrument in a simulated road with simulated pedestrians and other vehicles and so on. And then we can make hundreds of runs with that rare situation and make sure that we never fail. Or a dangerous situation, to have a near collision or driving very fast into a tight bend and so on. This you wouldn't want to do with a real vehicle, but we can simulate it and get an impression of how the real truck would behave. 1 hour takes 1 hour to drive if you have the real vehicle, but in a cloud cluster of a lot of computing power, you can run many hours of simulation in one wall clock hour. And that also adds to the coverage, to the increased coverage. If we can run more hours in an hour, complete more miles, if we can cover more kinds of vehicles in 1 minute, that is a good reason for going to simulations. And also analysis. If we look at the design and we make a conclusion that this variable can never take a value bigger than 2, then we can observe that in the code and be sure that it never happens, except if there is bit flips and so on, but that's another case that has to be catered for anyway, fault conditions. But having that kind of analysis makes a 100% coverage as opposed to just trying in by driving around or simulating. Repeatability is another aspect. If something, if there are problems that only occur in rare situations, it's very good to have a simulation, because then you can run the same simulation once again and see exactly which lines of code we're executing and why did this happen. I mean, typically when you do software development, this is not a problem, but with an embedded software system, what happens in the code depends on the outside temperature or the vibration from the road, or the how the steering wheel was turned quickly or slowly and so on. This is really difficult to repeat unless you have simulated those operations. And so that already touched on the next bullet, to have debugging. If we have a simulated system where we have access to the source code and all the timing, the operating system activities and so on, then we can pinpoint what goes wrong and how to fix it. If we only have a running truck with binaries executing on a ECU, on a computer, that is a lot more difficult to track and understand. Each truck is can be sold in a lot of different configurations, each truck range. And to make a test fleet that has both 6 wheels and 4 wheels, to have the high cab and the low cab, that has advanced cruise control installed and that haven't, and so on. All of that is a very big effort and maybe impossible. But if we do it in a simulation, it's possible to cover a lot more of these. And also maybe we are looking into making new combinations with a Renault gearbox put into a Volvo truck that has never been built before. We can make such a fixtures configuration and see if the simulation gives a good response, and then start changing the real configurations into that. Okay, so for testing, there are many good reasons for doing both real testing and simulated or virtual testing. And what implications does that have? What do we need in order to do the simulation-based testing? Because in general, we have both the driving of real truck, reviewing specifications, maybe proving and analyzing the specifications, simulating the vehicle content, and analyzing more from a physical approach. In order to do all these different engineering activities and rely on the outcome being valid, it means that whatever input the simulation guy is using, or whatever truck the test driver is driving, this must be representing the same design and the same product. Otherwise, the simulation is useless, or the analysis doesn't mean anything. So this will point in the direction of our modeling having to serve a lot of methods, but still having a consistent content. And these models, they are intending to represent the real truck with the binaries, the hardware, the traffic, the physical components. But we need to put it into some kind of machine-readable format models so that we can turn it into virtual trucks that we simulate or analyze. Also, whatever the engineers thought that this mechanical component, how they thought that it would behave in terms of its physical properties and so on, or on the complete truck level, they thought that the maximum speed or stopping distance or whatever was, we need to measure on the real truck in order to calibrate. So there's a loop here where we model things and continuously feed back the measurement results from the real product. But even so, it's not enough to put all of those measurements into an Excel sheet or something. We need to relate it to the real building blocks of the vehicle. So traditionally, there was something called V-model in the automotive industry or for systems engineering in general, that one start with some requirements and early phase expectations on the product. And after a long time, one go down into more details and start creating components. And those nuts and bolts and wheels and windscreens down here are gradually put together and we have a complete vehicle. We can still use the same analogy or the same model of thought when we go into a more modern approach. We have upstream expectations and requirements. We make code for the things that are software-based. We make models out of the mechanical things. And on that content, we are able to simulate and analyze and make sure that what we put in here is relevant. And then once we build the real binaries and we put them into the real ECUs and we evaluate the physical truck, that is a set of binaries and components that we can touch and try, and we can make sure that our result is consistent with what we are putting in. And in a continuous integration and deployment setting, this would mean that we very often and quickly go all the way down to a solution and experiment with it. We make a small change, go to a solution and experiment with it. So we can do this in the code and in the simulation-based approach every minute or hour. Maybe for physical trucks, we do that also on a daily basis, but there is a slight difference in what we can do, as I've already said. On the physical truck, we can do the physical evaluation and test driving from a more of a black box perspective. But on the code and on the models, we can do simulation, debugging, analysis, and have another perspective on our development. And depending on the amount of work or amount of analysis and rigor that we put in, maybe we do some of the work on every commit. Other things that is a more in-depth thing, for example, in the automotive world, one always do winter testing. One go to Arvidsjaur or some remote location and make sure that everything works, even if the road is slippery and even if the climate puts a pressure on batteries and moisture on the connectors and whatever. So that's something that happens a lot more seldom, but it's still part of the same iterative progression of the development work. So what I'm trying to say here is that models are required for all of this, both to do the simulation and analysis, obviously, but even for the physical truck, if we want to keep track of what happens with a test drive and a log outcome from an activity that we did, we need to relate all of that to some kind of ordered and structured information structure. And automation is, of course, highly important here. We cannot do this hourly or even by second integration, verification, feedback loops if things are handled manually, but rather we have a continuous integration flow where we put in code and models and automatically get the output. That's a real important capability. And another thing is that we were different teams with different aspects, I said before. And if we have a modeling approach that allows the different stakeholders to come together on the same description, then with a structure and behavior clearly defined, what are the interfaces between the parts, sometimes we are allowed to see inside the component and, for example, debug the code. Sometimes we have a supplier that only gives us a black box binary, but we know the external interface. So on this, this is what we as an OEM or vehicle manufacturer need to integrate and manage. And also, this is the intellectual property of the company. So we don't want to lose that engineering documentation. For example, just making the vehicles and creating the components, putting them together in the factory, but not having a proper description of the content. That doesn't help us when something goes wrong, or for the next iteration of the design when we want to add more functionality or make changes. This engineering information is a core asset for that purpose. And there are different vendors that make tools, of course, for this information, but that is a risk if we get the vendor lock-in and cannot change tools or change ways of working with our data. If the information is complex and intractable, that also is a stopper, because then we cannot use it efficiently. And when new engineers come in, they cannot make use of the data. So solid control of our engineering information is instrumental for that reason. And an important reason for using a model-based approach. Okay, so does anyone have any reflections or questions before I move to the next part, the what? I have tried to motivate why we need a model-based approach now.
I might recommend taking maybe a 5-minute break just to get everyone refreshed, and then come back at 2 o'clock.
Excellent. Okay, so my clock is 2.
Yep, let's go ahead and get back into it.
All right. So I'll talk a little bit about what is it that we need to model. Let's see. So one aspect is that we need to keep track of the vehicle content, in the sense that we don't care about how the height control or climate control or external lights are implemented, but we need to communicate with product responsible people about what are the properties of each of these, and which of them are included in a certain vehicle and so on. So the solution independent feature list, if you like. Another thing is the internals perspective on the vehicle content. We might have this layered architecture that I mentioned, that we on the high level just talk about the road to go from Göteborg to Borås, or the situation management to make sure that we are overtaking properly and choose the right lane, and all the way down to motion devices like brakes and electrical motors for propulsion. This perspective we need to have as well. This is where most of the development takes place. And we can see that as being residing on a certain software platform in the truck. And there is one of these stacks for the motion management, and maybe another one for climate control, and the third one for bodybuilder applications, meaning the extra equipment that crane builders or fire engines and so on put onto the vehicle. So application software needs to be managed and is part of what we model. We also need to, as I've argued before, manage virtual engineering aspects, not only delivering the real products, but also simulation and analysis content, in order to have deliveries instantly after having made code changes, to have enough confidence in what we verify, and the dangerous and rare events that also I mentioned before. So being more specific in what virtual engineering requires, we need to know the software, the application software itself, how the software platform behaves, how AD converters and other parts of the electronics work, sensors and actuators, physics, the vehicle dynamics or the temperature, thermodynamics laws and so on, and environment, what goes on in the traffic outside the truck. And all of this can be seen as a jigsaw puzzle, where we put together the pieces that are outside the vehicle and all the way into the core, to the application software. And if we do this properly, we can execute the pieces and simulate it in the truck. Some of it is the real production code in C or C++. Some of it is a simulation model of what a pedestrian does, or the curvature of the road where we are driving. So to manage this properly, we need to put together all the information in an architecture description language, because only then do we know how does the different pieces of information relate to each other. For example, if we have a software component that is related to and allocated to a certain ECU or hardware component, if we have a requirement that we need to check using some verification activity, all of this information needs to be properly organized and related to each other. And if we do that for a simulation scenario, we have something called model in the loop, where a model of the truck, electronics, the blue part, simulates together with a model of the mechatronics and mechanics, the green part, and together with the external environment. And we can swap the model part of the truck and exchange it with real software. Then it's called software in the loop. So here we are executing the real lines of C or C++ code, but we still don't have a real sensor or a real vehicle dynamics component and so on. All of that is simulated. And it's actually the same simulation here and here. So we can reuse the non-software part here. And in another phase or activity, we could take the computers, the embedded computers of the vehicle, that in reality are reading voltage and providing voltage, but we connect it to simulated sensors and actuators, and we make sure that when executing in our real ECU, as it's called, our real computer, then it behaves properly when we are simulating the rest. And of course, the next step is to take out all of this and put these ECUs into a real vehicle. But there is also another mode of operation, and that would be to take a real truck and rip out some of its functionality and instead have a prototype electrical system. For example, if we want to try a new way of automatic emergency braking, we can make a prototype of that and allow that prototype in the test track, obviously, to use the original brakes of the truck and then see how does the driver like that, or how is the performance and so on. So these are different simulation and execution technologies that need to be orchestrated. And that answers what to model if we look at a subset of everything. I think that's enough for now of what needs to be modeled. We can discuss how it can be modeled a little more in depth. And I mentioned here that we need the complete chain from a controller and through the mechanics and mechatronics and out to the environment. Because unlike games or word processors and so on, all the software that we are putting into a vehicle is reacting and acting together with physics. And therefore, we cannot deliver this software without having integrated and tested it thoroughly together with these physical parts. Doing it with software in the loop or hardware in the loop. Did you, are there problems with my link now? Or can you still hear me?
I can still hear you.
Good, because I got a warning that my internet is unstable. So how to model this in a way that properly takes care of the data flow? Well, we have this distinction between application software in different layers. And the upper layers take care of the general functionality, and lower layers, the concrete sensors and actuators, through the software platform and through the electronics and mechatronics of the environment. And the application software may read here a temperature, and that has a corresponding simulated temperature out here in the simulation of the physical phenomena. So that's the functional structure that we need to respect. We can also have this solution independent perspective where we just do a feature model and say that we have automatic parking, we have rain sensors, or the capability of automatic cleaning the windows. But we haven't said here in detail how that is realized in a functional architecture or a software architecture. And I'll come back to these feature models later when we talk about variability and configuration. Yes, so in order to put this functional chain into something concrete, machine readable, we can use a model where components have ports and interfaces, and they are connected to other ports. And on this basis, we have everything we need to do simulation. If we add some, let me go to that picture. If we add some behavior to the parts, if it's code, then it's the C code or C++. If it's something that is not software, then we need to have a simulation model for the same component. And then there is a FMU, function mockup unit concept that we can use. And together, some of these components in simulated behavior and some in source code can execute together. And in order to have something to check when we do that simulation, we can put in requirements and timing constraints, cost constraints, and other non-functional aspects on our system, and use that as our benchmark or as our checkpoint when doing simulation and analysis. So all of this needs to be put into that model-based structure. And one specific standard or approach for doing that description for automotive software is called AUTOSAR. The purpose in the beginning was that we wanted the ECUs to be less, how do you say, married to or hard-coded to their code. Because in the old days, one bought one of these computers and it had some software in it, but they were not possible to take apart. With the AUTOSAR standard, there is a software platform and the applications running on it can be moved between the ECUs at design time. So that means that our application components are more reusable and flexible. And there is a consortium driven initially by BMW and Mercedes, and basically all OEMs in the world are using this standard for their embedded code. And a more in-depth look on that structure. We have the operating system at the lower end towards the CPU and other hardware. And on the operating system, different sort of components are running. And as long as they are using the AUTOSAR interface to read and write data to be executed, triggered, and to report faults, to read sensor input and output and so on, then we can put these components, they are portable and can be deployed on other ECUs as well. That's the idea here. So looking at an AUTOSAR component, I think it's similar to what you saw before. There are these hardware independent software components. it sends out something, it receives something, and inside the components there are some runnables, which is similar to tasks, and that is where the actual code execution happens. Yeah, I'll skip this. Another part in the how is the non-software, or the functionality that our application software integrates to. And that can be represented using an add-on to AUTOSAR called ADL. And here there is things like the hardware topology with vectors and so on, and also a functional architecture. So if we have these brake controllers and wheel sensor software and so on, these software components need to integrate with platform software, with sound functionality, maybe AD converters, if I were to add that. Need to execute together with the environment outside the vehicle. And also we need to keep track of the physical architecture, which ECU is used for the various components and what sensors and actuators are connected to them. So both perspectives are needed to keep track of. So this is the allocation decisions. We can say triggering conditions for the different parts. Which modes are each of the components active in? All of these are things required to do the simulation. And sometimes the content of the components come from simulation tools like, or modeling tools like Simulink, and sometimes it is hard-coded. This is up to the respective engineer. And I mentioned the plant behavior. This can be modeled using this functional mockup unit concept. But unlike software where you are sending variables or variable data in API calls, when you simulate something like a torque or a speed, the information goes both ways. So you apply a certain pressure maybe in hydraulics and you get back a flow. So this means that models that capture physical behavior will look a little bit different than models that capture code and software behavior. Okay. 3 again, I would like to have a question just to keep you awake. Right. Not based on software. So this slide was made by some communication people that wanted to just take a sample out of the various technologies that we work with. But it turned out that in this sample there was quite a variety of technologies that were software-based. I think a lot of the votes were lost now, or what happened there, Greg?
I think so I see 46 of 68 have voted. And that looks like it's about
Okay.
stabilized. So I think that's 46 of the 68 are awake. We've got 53% of the vote is for 10, 43% for 20, and then 4% for 40.
Okay, so my update is a bit slower, but that's a good result, because out of these, it's only the wave piston that is not software based. And that's a good thing that it happened to be like this in the slide, because according to the various judgments and investigations, 90% of any innovation in the automotive industry is software based. So even the transmission here, automated manual transmission, has a heavy software content, because it is software that decides when to change gears. It reduces the speed of the engine. Then it moves the various parts of the gearbox into the right position. So even the ones that you think is a mechanical innovation is highly based on software. So that should be a inspiration for you to continue studies and make sure that, or be assured that what you do is highly interesting for us. So let's go back to the how part in modeling. So I wanted to say a few words about variability and product lines. And in the trucks that we deliver, it's 1.23 something on average that look the same. Otherwise, there is a difference in wheelbase or number of axles or the functionality of the driver support system and so on. So if we make 100,000 trucks, then very few look the same. And not only the truck itself has a huge configuration space, also the engineering information that we use to build it obviously must follow the same variation space and more, because we may have a lot of different tests on a certain truck in different variants. We may have different timing annotations that is variant controlled. So it's really important for us to be able to manage this properly. And when doing that, anything we do has a mechatronic part, or almost everything. So it means that if we change the number of wheels or the way the brake actuator works, we must also change software accordingly. So variation in software and electronics must be consistent with variation in the mechanical component. Some of that variability is visible to the customer. Let's say the number of wheels or the driving support function included. But they don't care about if we have this or that cable or using this or that actuator. So that is more of a technical variability internal to the designers. And also, even as an engineer, depending on what you do, maybe you don't need to know all the internal variability of a certain domain. You care about some variability, but not all of it in detail. So this is something to bear in mind when thinking about product lines and variability. And we have two typical mechanisms. Our feature model says that some functionality is included. It relies on certain ECU maybe and software component and other related software components and hardware components. If we take away that feature, then we also take away the component. So this is one variability mechanism. An example is if we have lane keep assist that relies on cameras. So if we have a vehicle where we take out the lane keep assist feature, then also we take out the cameras and corresponding software. Very often, instead, we are using parameterization. So we have an optional functionality, for example, lane keep assist. We always use camera, but for other purposes. So that means that we don't take out anything, we just change a parameter to say our lane keep assist function is not available. Taking out the functionality means that we change parameter values. And the reason why this is typically used is because then we can have the same software for all of our vehicles. We only change parameterization and say that this is available, this is not available. For other software, maybe there's a parameter that characterizes or calibrates functionality. For example, if the thing that went away here was automatic, then maybe instead of being maximum height 12, this ride height will be only 8. So it's a way to keep track of the track configuration in all of the parts of the software. And the third variability mechanism I want to mention is that sometimes we have inside a domain or a component some variability that depends on external decisions. So if we make a general software component for wiping control, it might be useful both for front wiping and rear wiping. But when we put this into use, maybe we don't care about the internals. So we say that we have a wiper controller, it can be used for front and rear. It has these inputs and outputs, and it has this threshold value that you can influence. But we don't expose how that is done. Then this is a way to organize the variability in a stepwise manner. So maybe on the top, we are just talking about which market is this vehicle for, or which model range or trim level do we have. That means on the body domain that we may have cruise control with a short range or long range. This might mean for the cruise control that it is adaptive or not. So we expose the variability where we need to see it. Because otherwise, managing variability might become overwhelming, and the wrong people would have to deal with all the details. The last how topic I wanted to mention was the engineering workflow. So ideally, we would like to have this continuous integration and deployment workflow where you make a small change and you immediately get the result of that. And then we need to start with modeling and coding, including modeling the variability. Then we resolve and take away all the content that is not relevant for our configuration and assign parameter values that are according to our configuration. We are now down from a 150% product family scope into 100% single vehicle scope. And we can then generate what is required, for example, for a simulation or analysis, or even for the physical product and the binaries that it requires. And having generated, we can do the simulation or analysis, either looking at software only, for example, with unit testing or integration testing. But we can also integrate with physics and have the simulated mechatronics and vehicle dynamics and traffic and so on. And there are other analysis and verification activities that we might want to do. And depending on what we want to do here, the generators will look differently, obviously. So having this 150% representation, where in the example of simulation, we can have our application software on the one hand and simulations of the traffic on the other. We need to do the configuration of each of these parts. And as I mentioned, for software, we are selecting and parameterizing software components. For a simulated wheel or a simulated sensor or something else, non-software, we would select which components to include and also give parameters to those simulation models, whether to simulate a heavy wheel or a light wheel, a big wheel or a small wheel, and so on. And finally, for the environment, we can have a scenario description for what should happen and a road description to say we want to try a narrow rural road, or we want to go onto the highway, and so on. So having parameterized the parts of the simulation, we can then create, in the case of a certain simulator, binaries that can run from application software, from the physical and environment content, and put it onto our simulation platform. And all of the simulation platform will then mimic the real truck, and we can run our tests, making a test stimuli and check the response. So it starts with input data of various forms, and where you make the changes, and then the automatic variability resolution, automatic invocation of the generators and simulations, and then the test activities. And this can be done in the local, on your local PC or in a cloud. So I mentioned this because this workflow cannot be achieved if we don't have an appropriate model-based approach. Without it, it's not possible to weave together the different parts here of the truck into something that is simulable. You don't know how to generate the different parts. You don't know which tests to run, and so on. So that would be my conclusion, that we need a way to define the software, and AUTOSAR software platform is a de facto standard that is used for the application software. And inside those components, of course, traditional C code and C++ and the things that you are mastering are used. For things that are not software, we need to capture requirements and variability, test information, timing, safety, all of those aspects of hearing data. We can do that with an EAST-ADL model. And because of having such a framework for the model-based approach, different people can understand the engineering information and exchange it, and tools and methodology on that representation can evolve. So the final slide is a kind of motivation causality. We want to have new vehicle functionality and increase our development efficiency. This requires shorter lead times and an iterative and incremental development, because without this, our development is not going to be efficient. You probably heard it a lot of times that a short feedback cycle is important, because if you make coding and changes and it takes many days and weeks before you get the result of that, then you have already forgotten what you were doing. So rather you would like to have immediate feedback on what you're doing. And that requires engineering automation. Things must be done automatically in a DevOps chain. But doing that for just code might be possible, but doing it for an embedded system or an automotive system with all the different information and components that are interacting is not easy. So we need to represent and automatically configure that, and automatically being able to evaluate it using simulations or analysis. And that finally calls for a way to variability, to represent the software and electronics and mechatronics, and also the vehicle dynamics and multiphysics. That is what the customer really care about. Do I stop when I press the brake pedal? Do I consume less energy than my previous vehicle, and so on? Okay, so I stop there for questions or comments.
Yeah, if you have any questions, please put them in the chat, and I would definitely encourage you. We have a few minutes left before the end of class. This is a great chance. If there's anything you have questions about on the content covered, on practices at Volvo, industrial practices in general, this is a really good chance to do that. So I guess I will throw in something here, and what I'm curious about for students, what do you think are some of the most important skills to learn in regards to development if they're interested in working in trucks or automotive design?
Yeah, I mean, what is needed is talent and interest and commitment. So it's not easy to get away from that. I mean, you can learn these technologies, but if you don't have that mindset, then it doesn't help. On the other hand, if you become a good programmer and a good software engineer and good software architect, then you don't need to have any specific automotive skills usually. I mean, we have the mechatronics and mechanics aspect of it that some of us need to master, but many of us are just doing like tool development in this simulation environment, and actually don't need to know anything about oil and diesel. Others are preparing tests that are measuring, trying to evaluate, does the new truck excel over the old one? They They need to understand customer expectations and how to define metrics that characterizes it and so on. So it's a wide scale. And for a software engineer student, I think focus on what you're best at, and that is something that we will need increasingly.
What do you see as some of the biggest changes coming in the next few years?
Yeah, I didn't cover much of that here. I only mentioned in the beginning that we have these challenges coming with new architectures and new control strategies. I mean, automation, connectivity, and electrification, these are more on the outside, so to say, and is only indirectly related to software. But these last two bullets have big impact on the software development. And there is one big change, that is that we are going from a traditional signals-based software architecture into a service-based architecture. We're moving from C programming with resource-constrained automotive embedded computers into C++ and a computing environment that looks more like a desktop computer. So that is a big change that it is coming, and at the same time it still have the constraints of the old vehicle, so to say. We still have safety, still have energy consumption, we still have expectations on climate control and other things in the multiphysics domain. So this combination of evolving software technologies with the physics and mechatronics and electronics constraints of the vehicle is an interesting challenge for the automotive domain.
We have a couple of questions from students in the chat too, so we'll go ahead and get those in there as well. So I don't dominate the whole time. So Raul Kent asks, how are the details of the tests created? Are they generated to see within which range of stimuli the system behaves as intended, or just in general, how are the test details created?
I mean, in the literature and in state-of-the-art tools and so on, there is one palette of approaches. You can generate the tests using state space exploration of the intended execution behavior. You can use machine learning methods or AI to gradually explore behaviors and create tests through that kind of automatic methods. And yeah, there's a long range of approaches. Maybe for us, it boils down to two kinds of tests. One is where we are looking concurrently on invariants. So we are checking that these behaviors are always there, or these behaviors are never there. For example, always when the brake pedal is in this angle, there is a retardation request. Or never when we are in speeds over 30 is the parking brake applied. So that's the invariant testing. And the other category is scripted testing, where we automatically make a stimuli and check the response, make stimuli, check response. That's if we talk about auto. And then we have something called exploratory testing, where drivers and test experts try to break the systems. So they do unusual things in order to find flaws in the system.
We have a student who shares your name, Henrik, who's asking, which market is easiest to build for? Does it vary a lot between external demands like US laws versus EMEA laws that affect the software in those products?
The question was if the software varies a lot between.
Yeah, is there a variation between different markets, it looks like building a product for release in the US versus Europe versus Middle East and so on?
Yeah, I mean, there is the ambition, and also in practice, we are using a joint product line where in the US, when you have these nose trucks, that looks very different from the European trucks. But under the hood, they are using the same ECUs and buses and software, obviously with different parameterization and calibration, but there is a huge commonality between these. And over time, I mean, over the years, it started with only Volvo trucks, and then we have purchased other brands. And over time, more and more of the internals of these become the same.
Are there any other questions? So there is here student Joel Rudsberg mentioned, you've mentioned that C and C++ are mainly used. They're wondering, do you use any functional programming languages at Volvo? And in a project, how are programming languages chosen depending on the product?
Yeah, I think traditionally we didn't have a choice in programming language because the ECUs or the computers, they were highly cost optimized. So limited memory, limited CPU capacity, and so on. So it was always C. But recently, one also used C++ and even Java for some domains. Functional programming, I don't think is used. That is dependent on a number of things. If you have a certain domain that is more suitable for a certain programming language, you might choose that. But yeah, the variation is so low. We only have 2 or 3 languages to choose from in practice. So it usually ends up with C, and for old or legacy platforms, and for new development, C++ is very much on the increase.
Great.
Maybe there's also a difference between the domains in powertrain and chassis and the more safety critical areas. There's a slower take on towards C++ compared to infotainment and telematics.
All right, any last questions? We have about 10 minutes left. If anyone has anything. I'll give it just a second here. All right, it looks like we might not have anything. I would definitely like to once again thank our guest speaker for coming in today. I think this is a super interesting talk, and I think very relevant to all the things we've been talking about in this class. If any of the students, if any of you have any additional questions you want to ask, you can feel free to email those to me and I can pass them along. Otherwise, I think we're about done for today. Next class, we'll talk about feature model analysis. Make sure you're working on that assignment that's due Sunday, and feel free to send us any questions or ask on Canvas if you have any. But yeah, otherwise, I think we'll go ahead and wrap up for today. Thank you again, Henrik, for coming in. This was really fun.
Okay, thanks for having me and for listening.
Okay.